apparent power, measured in volt-amps, is the vector sum of real power, measured in watts, and reactive power, measured in volt-amps reactive. For a simple resistive load, the reactive power is close to zero. This means the apparent power is approximately equal to the real power. Therefore, you should not connect a load to the transformer that draws more than 20 watts. Exceeding the 20 volt amp rating, which can be approximated as 20 watts in this case, can cause the transformer to overheat and potentially fail. The transformer's volt amp rating indicates the maximum apparent power it can safely deliver without overheating. Apparent power is a measure of the total power a circuit uses, including both the power that performs work, real power, and the power that is stored and released in reactive components like inductors and capacitors. Reactive power, real power, measured in watts, is the power that actually does work in a circuit, such as lighting a bulb or turning a motor. Reactive power, measured in volt-amps reactive, is the power that is stored and released in reactive components. It doesn't do any real work but contributes to the overall current flowing in the circuit. In a purely resistive circuit, where there are no inductors or capacitors, all the power is real power, and the apparent power is equal to the real power. However, in circuits with reactive components, the apparent power is always greater than or equal to the real power. The difference between apparent power and real power is the reactive power. Transformers are rated in volt-amps because their ability to deliver power is limited by the current they can handle without overheating. The current is determined by the apparent power, not just the real power. Even if a load has a low real power consumption, it can still draw a significant amount of reactive power, which increases the total current flowing through the transformer and can cause it to overheat. To avoid overloading a transformer, it's important to ensure that the total apparent power of the load connected to it does not exceed the transformer's volt-amp rating. This can be done by calculating the apparent power of the load using the following formula: apparent power equals voltage times current. Alternatively, if the real power and reactive power of the load are known, the apparent power can be calculated using the following formula: apparent power equals the square root of real power squared plus reactive power squared. In many practical situations, especially with small transformers powering simple devices, the reactive power is relatively small compared to the real power. In such cases, it's often reasonable to approximate the apparent power as equal to the real power. However, it's always best to err on the side of caution and use the more accurate formula if possible. In the case of a 120 volts primary to 24 volts secondary transformer rated at 20 volt amps, the maximum current the secondary can supply is calculated by dividing the apparent power by the secondary voltage. This gives 20 volt amps divided by 24 volts, which equals approximately 0.83 amps. Therefore, any load connected to the secondary should draw no more than 0.83 amps. If the load is purely resistive, then the power dissipated by the load can be calculated using the formula power equals voltage times current, which in this case is 24 volts times 0.83 amps, which equals approximately 20 watts. However, if the load is not purely resistive, then the apparent power will be greater than the real power, and the load may draw more current than the transformer can safely handle, even if the real power is less than 20 watts. To ensure that the transformer is not overloaded, it's important to measure the actual current drawn by the load using an ammeter. If the current exceeds 0.83 amps, then the load should be reduced or a larger transformer should be used. It's also important to consider the operating environment of the transformer. If the transformer is located in a hot or poorly ventilated area, it may overheat even if the load is within its volt-amp rating. In such cases, it may be necessary to direct the transformer or provide additional cooling. In summary, the volt-amp rating of a transformer indicates the maximum apparent power it can safely deliver without overheating. To avoid overloading a transformer, it's important to ensure that the total apparent power of the load connected to it does not exceed the transformer's volt-amp rating. In many practical situations, it's reasonable to approximate the apparent power as equal to the real power, but it's always best to err on the side of caution and use the more accurate formula if possible. The maximum current the secondary can supply is calculated by dividing the apparent power by the secondary voltage. It's also important to consider the operating environment of the transformer and derivate it if necessary. Here are some additional details about transformer ratings and considerations for avoiding overloads. Firstly, understanding volt-ampere versus watts. Volt-ampere is the apparent power, the product of volts and amps. Watts is the real power, the power actually consumed by the load. The difference arises from reactive loads like motors or capacitors, where current and voltage are out of phase. Transformers are rated in volt-amperes because the heat generated in the transformer is proportional to the volt-amperes, not just the watts. Secondly, power factor. The power factor is the ratio of real power watts to apparent power volt-amperes. A power factor of 1 indicates a purely resistive load, where volt-amperes equals watts. A power factor less than 1 indicates a reactive load. When selecting a transformer, it's important to consider the power factor of the load. If the load has a low power factor, the transformer will need to be larger to supply the same amount of real power. Thirdly, transformer loading. Avoid continuous operation at the transformer's maximum volt-ampere rating. It's good practice to leave some margin for safety and to account for potential increases in load. Overloading a transformer can lead to overheating, insulation breakdown, and ultimately, failure. Fourthly, inrush current. Some loads, like motors and transformers themselves, can draw a large inrush current when first energized. This inrush current can be several times the normal operating current. The transformer must be able to handle this inrush current without excessive voltage drop or overheating. Fifthly, ambient temperature. The ambient temperature affects the transformer's ability to dissipate heat. Transformers are typically rated for a specific ambient temperature, such as 40 degrees Celsius. If the ambient temperature is higher, the transformer's volt-ampere rating must be derated. Sixthly, altitude. At higher altitudes, the air is less dense, which reduces the transformer's ability to dissipate heat. Therefore, transformers used at high altitudes may need to be derated. Seventhly, harmonic distortion. Non-linear loads, such as electronic devices, can generate harmonic currents that distort the voltage waveform. These harmonic currents can increase the losses in the transformer and cause it to overheat. If the load is known to generate significant harmonic distortion, a special K-rated transformer may be required. Eighthly, transformer efficiency. Transformers are not 100% efficient. Some of the power is lost as heat due to core losses and winding losses. The efficiency of a transformer is typically around 95% to 99%. Ninthly, safety factors. Always include a safety factor when selecting a transformer. A typical safety factor is 25% to 50%. This means that the transformer's volt-ampere rating should be 25% to 50% higher than the actual load. Tenthly, example calculation. Suppose you have a load that draws 10 amps at 24 volts and has a power factor of 0.8. The apparent power is 24 volts times 10 amps equals 240 volt amperes. The real power is 240 volt amperes times 0.8 equals 192 watts. You would need a transformer with a volt-ampere rating of at least 240 volt amperes. To include a 25% safety factor, you would need a transformer with a volt-ampere rating of 240 volt amperes times 1.25 equals 300 volt amperes. Let's delve further into the technical aspects related to transformer VA ratings, focusing on practical implications and calculations first. Understanding transformer construction. Transformers consist of 2 or more coils of wire wound around a common ferromagnetic core. The primary winding is connected to the source voltage, and the secondary winding is connected to the load. The ratio of the number of turns in the primary winding to the number of turns in the secondary winding determines the voltage transformation ratio. Second, transformer voltage and current relationships. The voltage and current in the primary and secondary windings are related by the following equations. Voltage primary divided by voltage secondary equals turns primary divided by turns secondary, and current primary divided by current secondary equals turns secondary divided by turns primary. These equations assume an ideal transformer with no losses. Third, transformer impedance. The impedance of a transformer is the opposition to the flow of alternating current. The impedance is determined by the inductance of the windings and the frequency of the alternating current. The impedance of the primary winding is typically much higher than the impedance of the secondary winding. Fourth, transformer losses. Transformers are not perfectly efficient, and some of the power is lost as heat. The main sources of transformer losses are coil losses and winding losses. Coil losses are caused by hysteresis and eddy currents in the core material. Winding losses are caused by the resistance of the windings. Fifth, transformer regulation. Transformer regulation is a measure of the change in secondary voltage from no load to full load. The regulation is expressed as a percentage of the no load voltage. A transformer with good regulation will have a small change in secondary voltage from no load to full load. Sixth, transformer efficiency calculation. The efficiency of a transformer is calculated as the ratio of the output power to the input power. The efficiency is typically expressed as a percentage. The efficiency of a transformer is typically around 95% to 99%. Seventh, transformer cooling methods. Transformers generate heat due to losses in the core and windings. The heat must be removed to prevent the transformer from overheating. Transformers are typically cooled by air, oil, or water. Air-cooled transformers are used for smaller applications. Oil-cooled transformers are used for larger applications. Water-cooled transformers are used for very large applications. 8. Parallel operation of transformers. Transformers can be operated in parallel to increase the capacity of a power system. When transformers are operated in parallel, they must have the same voltage ratio, impedance, and polarity. 9. Autotransformers. An autotransformer is a type of transformer that has only one winding. A portion of the winding is used as both the primary and secondary winding. Autotransformers are typically smaller and less expensive than two-winding transformers. However, autotransformers do not provide electrical isolation between the primary and secondary windings. 10th, three-phase transformers. Three-phase transformers are used to transform three-phase power. Three-phase transformers can be connected in a variety of configurations such as delta-delta, delta-Y, Y-delta, and Y-Y. The choice of connection depends on the application. Let's discuss practical scenarios and troubleshooting related to transformer VA ratings and potential overload situations. Firstly, load monitoring. Regularly monitor the current drawn by the load connected to the transformer. Use an ammeter to measure the current under normal operating conditions. This helps in identifying any unexpected increase in load that could lead to an overload. Secondly, thermal monitoring. Monitor the temperature of the transformer. Use a non-contact infrared thermometer to check the temperature of the transformer's core and windings. Excessive heat is a sign of overload or other problems. Thirdly, voltage drop. Check for excessive voltage drop on the secondary side of the transformer. A significant voltage drop under load can indicate that the transformer is being overloaded. Fourthly, harmonic analysis. If the load includes nonlinear devices, perform a harmonic analysis to determine the level of harmonic distortion. High harmonic distortion can increase the transformer's losses and lead to overheating. Fifthly, insulation testing. Periodically perform insulation testing on the transformer windings to check for insulation breakdown. Insulation breakdown can lead to short circuits and transformer failure. Sixthly, oil analysis. For oil-filled transformers, perform oil analysis to check for contaminants and degradation of the oil. Contaminated or degraded oil can reduce the transformer's cooling capacity and lead to overheating. Seventhly, proper ventilation. Ensure that the transformer has adequate ventilation to dissipate heat. Remove any obstructions that could block airflow around the transformer. Eighthly, fuse protection. Use appropriately sized fuses or circuit breakers to protect the transformer from overload and short circuits. The fuses or circuit breakers should be sized according to the transformer's volt-ampere rating and voltage. Ninthly, surge protection. Install surge protection devices to protect the transformer from voltage surges caused by lightning or switching events. Voltage surges can damage the transformer's insulation and lead to failure. Tenthly, regular maintenance. Perform regular maintenance on the transformer, including cleaning, inspection, and testing. Regular maintenance can help to identify and correct potential problems before they lead to transformer failure. Let's elaborate on specific transformer types and applications, connecting the VA rating to their functions first. Control transformers. Control transformers are used in industrial control circuits to provide a stable voltage for control devices such as relays, contactors, and timers. These transformers typically have low volt-ampere ratings ranging from 50 volt-amperes to 1000 volt-amperes. The volt-ampere rating must be sufficient to supply the power required by all of the control devices connected to the transformer. Second, isolation transformers. Isolation transformers are used to isolate sensitive electronic equipment from the power line. These transformers provide electrical isolation between the primary and secondary windings, which helps to reduce noise and improve safety. Isolation transformers typically have volt-ampere ratings ranging from 100 volt-amperes to several kilovolt-amperes. Third, step-up transformers. Step-up transformers are used to increase the voltage from one level to another. These transformers are commonly used in power transmission systems to increase the voltage for long-distance transmission. Step-up transformers can have very high volt-ampere ratings ranging from several kilovolt-amperes to several megavolt-amperes. Fourth, step-down transformers. Step-down transformers are used to decrease the voltage from one level to another. These transformers are commonly used in distribution systems to reduce the voltage for use by residential and commercial customers. Step-down transformers can have volt-ampere ratings ranging from several kilovolt-amperes to several megavolt-amperes. Fifth, rectifier transformers. Rectifier transformers are used in rectifier circuits to convert alternating current to direct current. These transformers typically have special design features to handle the non-sinusoidal currents produced by the rectifier circuit. Rectifier transformers can have volt-ampere ratings ranging from several kilovolt-amperes to several megavolt-amperes. Sixth, inverter transformers. Inverter transformers are used in inverter circuits to convert direct current to alternating current. These transformers typically have special design features to handle the high-frequency currents produced by the inverter circuit. Inverter transformers can have volt-ampere ratings ranging from several kilovolt-amperes to several megavolt-amperes. Seventh, audio transformers. Audio transformers are used in audio circuits to match the impedance of different audio components. These transformers typically have low volt-ampere ratings ranging from a few volt-amperes to several volt-amperes. Eighth, instrument transformers. Instrument transformers are used to measure high voltages and currents in power systems. These transformers provide electrical isolation between the high voltage or high current circuit and the measuring instrument. Instrument transformers typically have very low volt-ampere ratings ranging from a few volt-amperes to several volt-amperes. Ninth, welding transformers. Welding transformers are used to supply the high current required for welding. These transformers typically have special design features to handle the high currents and voltages required for welding. Welding transformers can have volt-ampere ratings ranging from several kilovolt-amperes to several megavolt-amperes. 10th, specialty transformers. There are many other types of specialty transformers designed for specific applications. These transformers may have unique design features and volt-ampere ratings depending on the application. Remember to consult the manufacturer's specifications and relevant electrical codes when selecting and installing transformers for any application. Safe practices are essential to prevent electrical hazards and ensure the reliable operation of electrical systems.